In the last video, I talked about how a current carrying wire creates a magnetic field, which effectively turns the wire into a magnet. So if the wire becomes a magnet, that means it's going to experience magnetic forces from other magnets. Now, the mathematics behind what's happening is another mathematical equation. It's kind of a plug and chug. FB, force magnetic field, equals BIL sine theta. We aren't going to worry about the sine theta a whole lot in here. More often than not, it's going to turn into a 1 because it'll be 90 degrees. The other thing worth noting is we'll often be concerned about what is known as force per meter, or F over B equals Bison, BI sine theta. Again, that's sine theta going to 1. The reason why we are often more concerned about force per meter is because if you have a wire that's many miles long, you're really only concerned about how to support that wire through various sections of it. To identify these variables, F with the subscript B, that is the magnetic force. All forces are measured in newtons. B, as you learned in the last video, is the magnetic field. Magnetic field is measured in Teslas. I is the current. What made the wire magnetic to begin with was having current in it. L is the length of the wire, and the length is in meters. Now theta, well, where does theta come into play with this? So if I have a wire carrying current in this direction, and here's my magnetic field kind of going up and to the right, theta is the angle shown here between the magnetic field line and the wire. I'm going to go ahead and delete this image really quick. If you want to take a deeper look at it, just pause the video. So let's solve some of these practice problems. The magnetic force per meter, so force per meter on a wire with 15 amps is exposed to a 5 millitesla field. So I'm going to do force per meter BI sine theta. The sine of theta is 1. This here says maximum force. The sine of theta, for those of you who aren't aware, so the sine of theta is always going to come out to be a number that is greater than or equal to 0, but is less than or equal to 1. So sine of theta bounces between 0 and 1. So if I want the maximum, I want this to be equal to 1. So the force per meter is the 5 e negative 3 because it's milliteslas, times the 15 amps. So 5 e negative 3 by 15 gives me 0.075 newtons per meter. Next example, what is the maximum force on a 6 centimeter long wire that has a current of 20 amps and exposed to a 20 microtesla field? Again, we're looking at maximum, so we are going to set the sine of theta equals 1. But this time, instead of looking at force per meter, I am just looking for the force itself. So this would be 20 e negative 6, I is 20, and L is 6 centimeters. We have to convert that to meters, so 0.06. There you go, 20 e negative 6 by 20 by 0.06. The result is 2.4 e negative 5 newtons. Now, if a wire is really, if it's carrying current, it's really just a vessel for charges to move. So that means it's the motion of the charges that's truly creating the magnetic field for the wire. So our next bit to look at is, well, does that mean an individual charge moving through a magnetic field will experience a force? And the answer is yes. Now, if we're talking about an individual charge, we're not going to have a wire with length and current. We're going to have a charge, a particle with a charge and a velocity. So the equation is QVB sine theta. Again, more often than not, that's going to turn into a 1. And my examples today talk about maximum force, maximum force. And similarly, again, if I have a charged particle and it's moving this way to the right, and there's a magnetic field up and to the right at this angle shown, theta would be the angle between that magnetic field and the velocity of the particle. To identify your variables really quick, FB, that's your magnetic force, just like in the previous equation, measured in newtons. Q is the charge of our particle, that's measured in coulombs. V is the velocity of the particle, that's measured in meters per second. And B is the magnetic field strength, measured in Teslas. So, question 3, what is the maximum force on a proton that is moving at 30,000 meters per second through 5 Tesla magnetic field? The other piece of information here is the word proton. That's some given information. The maximum force tells us that the sine of theta will be 1, and the proton tells me what my charge will be. So QVB sine theta, the sine of theta is going to 1 to maximize this. The magnetic force will equal Q. A proton has a charge of 1.6 e negative 19. The velocity given is 30,000. And we have a 5 Tesla field. So go to the calculator, 1.6 e negative 19 times 30,000 times 5. I got 2.4 e negative 14. So 2.4 e negative 14 newtons is the magnetic force. Example 4, what's the maximum force on a 6 microcoulomb charge moving at 12,000 meters per second through a 4 Tesla field? Again, maximum force tells me the sine of theta is going to 1. So the force will be 6 micro is e negative 6, times 12,000 meters per second through a 4 Tesla field. 6e negative 6 times 12,000 times 4. And the result is 0.288 newtons. The last thing is, well, what's the direction of everything that's happening? And this is where we get what we call the FBI gun law. And the reason why it's called FBI gun law is F stands for force, B stands for magnetic field, and I stands for current. And then the gun law comes in because you kind of shape your hand like a pistol, as you see here. Now, obviously the middle finger you can see is not tucked in. It's pointing 90 degrees away from the index finger. Your thumb represents the magnetic force. Your index finger represents the direction of the moving charge or the direction of the current. And your middle finger represents the direction of the magnetic field. So it's a matter of getting your hand. You'll be given 2 of these things, and your job will be to solve, well, where is the third one? In this particular case, you could see the moving charge is going to the left, and the magnetic field is sort of coming out of this screen, and that leaves your thumb pointing upwards. This will work for a current carrying wire. This will work for a positive charge, but a negative charge will be slightly different. A negative charge, since it's opposite signs, you're going to use your opposite hand. So you'll do the same thing, but you'll do it with your left hand.